Hey chemists, let's pick up at chapter 7, chemical bonding and molecular geometry. So let's remember in chapter 6, we talked about electronic structure, and one of the skills that I wanted you to master was writing out electron configurations of the different elements. So we'll definitely be using that skill in chapter 7. So in this chapter, we'll be looking at different types of bonding descriptions like ionic and covalent bonding. Together with those types of bonding descriptions, we will be writing out Lewis structures. So here is where our ability to make electronic electron configurations will really come in handy. From there, we will look at formal charges and resonance structures of different covalent compounds. And then we will look at the strengths of ionic and covalent bonds. So that depends on the electronegativity of the atoms that are involved in that specific molecule. So I split this chapter into two parts just so I can try to roll out these videos as fast as I can. And so I split this into two parts. So these first 5 points will be part one that I will go over in this video. And then finally, part two is molecular structure and polarity. So that's like the back half of the chapter. All right, so let's get started. So the types of bonding that I talked about that in the outlined chapter, I will just define some of those right now. So we haven't really talked a lot about metallic bonding yet, but I'll just define it here because it is one of the types of bonding that we can see in different arrangements of atoms. Um, so in a compound that exhibits metallic bonding, metals are bonded to several other metals of typically the same type, unless you have an alloy. Um, so electrons in metallic types of bonding, where each atom is connected to multiples of each atom, the electrons are the important thing here to note is that the electrons are delocalized, and move through the entire structure. So this is why we say that metals conduct electricity, because those electrons are delocalized, that the electrons on one specific atom is it's not so one electron is not, let's say, connected to one specific atom. It's delocalized across a large portion of the actual substance itself. um, so if you would put in some type of electrical bias across a piece of metal or put an electrical current through it, those electrons can move through the structure because no electron is permanently bound. I guess that's what I was trying to say. Electrons are not permanently bound to any one atom. Um, Electrons are delocalized and move around the entire structure. So this is why we say that, metals are conductive. Conductive. So here is a picture of some generic crystal structure of a metal that exhibits metallic bonding. So if you see this central atom, this can be any metal, it could be like titanium or something. So this central atom is actually has a metallic bond between 1, 2, 3, 4, 5, 6, 7, 8, 8 different atoms. So these are eight. That central atom has 8 metallic bonds. And this is what we mean by metal atoms are bonded to several other atoms. So the next type of bonding description we want to talk about is ionic bonding. We have had plenty of experience with ionic bonds when we identified these kinds of compounds when we were naming. We know that we name ionic compounds when we have a metal cation, and a non-metal anion. And then in chapter 6, we actually saw that the electron affinity for nonmetals make them tend to produce anions, while the low ionization energies of metals tend to have them become cations. So we have an ionic bond when we have a cation and an anion, and we call that an electrostatic attraction between those ions. So with this first point, we have an electrostatic attraction when we have a positively charged cation and a negatively charged anion. And then what I wanted to say here is that these ions are formed by a transfer of valence electrons. I'll write it out. Or electrons. So either one or more. So maybe if I show you an example here. So if we have a neutral sodium atom and a neutral chlorine atom, we know that a substance that has both sodium and chlorine typically forms sodium chloride, the ionic compound. But right now I have them just written as their neutral substances. So what happens when we produce the ionic compound and produce the ionic bond, we have to make first a cation and anion. Right now we just have two neutral atoms. There is no attraction between one of them or either of them. So what drives the formation of an ionic compound is this transfer of valence electrons. So here is where our use and skill of electron configurations come into hand. So if we write out the electron configurations for sodium and chlorine, we can more clearly see this transfer of electrons to form an ionic bond. So the electron configuration for sodium is neon, has a neon inner core, and a lonely 3s1 electron. So sodium is 1, it's a metal, and metals tend to have low low in general ionization energies. So this is evident by sodium's electron configuration. Sodium's first ionization energy, I can guess, is going to be pretty low because there is a lonely electron, a lonely valence shell electron. That's why when we see sodium as a ion, it is typically in the form sodium plus 1. We will almost never see a sodium plus 2 because that second electron has to come from this neon core, and that's not going to happen. All right, so that's the electron configuration for sodium. Now let's look at it for chlorine. So chlorine also has a neon core. It has a 3s1, 3p5. So what you see here is that the neutral chlorine atom has an incomplete, oops, not 3s1, it's 3s2. 3s2, 3p5. All right. So chlorine has a incomplete valence shell that in order to get a noble gas configuration, chlorine needs to gain one more electron in its p shell. So you can see that here. It's 3p5. So chlorine is going to tend to gain one extra electron to become chloride. And so when we see chlorine in ionic compounds, we typically see it as a Cl minus. So you can kind of clearly see that when you bring a neutral sodium atom and chlorine atom together, that this sodium is going to very easily lose that 3s electron. And what it's going to do is that electron is going to transfer to chlorine. So essentially, you have this electron transfer happening between sodium and chlorine. An ion is formed by a transfer of valence electrons. Sodium is going to lose one of its valence electrons and it's going to be gained by chlorine. And what you have overall after that event happens is now you have a sodium plus cation because sodium lost an electron, and you have a chlorine minus anion chloride. And now both of these substances have a noble gas, chlorine is argon, noble gas configuration. So I just try to really step by step explain why this happens, but I think for most of you, you kind of already know that this happens, that sodium, because where it is on the periodic table, loses one electron, chlorine gains one. So if you bring them together, you'll get a sodium plus, a chloride minus, and have sodium chloride. So you do have some experience there, but I just kind of step by step showed you how that works. All right, so we talked about metallic bonding, ionic bonding, and then lastly is covalent bonding. So covalent bonding, this is the organic realm. So if you stick with it with chemistry and take organic chemistry at some point, you will be definitely involved with dealing with covalent bonding at that point. But how we define it, covalent bonds involves sharing of electrons between atoms. Ionic bonding, there was just a complete 100% transfer of electrons. But with covalent bonding, atoms tend to share those electrons because their electronegativities are similar. And we'll talk about that in later slides, but I'll just let you know now. And what I wanted to say here is that atoms join through sharing of valence electrons. So from this slide, you should just definitely know, since we're mainly going to be talking about ionic bonding and covalent bonding. Ionic bonding has a transfer of valence electrons, so then we form cations and anions, while covalent bonding, two adjacent atoms will just share electrons, share their valence electrons, and we'll see why this is necessary, and it has to do with the octet rule, and I think we'll get there in later slides. So let's keep going. So let's talk about Lewis dot structures or Lewis dot symbols of atoms. So this closely relates to electron configurations. You need to have a really strong skill set of electron configurations in order to do Lewis dot structures correctly. So with Lewis dot structures, we are only going to care about the valence shell electrons of that electron configuration that you've made. So I think it's just best to just do an example. So if we take calcium, let's just write out its whole electron configuration. So for calcium, it is, let's just write the whole thing. So 1s2, 2s2, 2p6. Oh, we have to go to 20. 3s2, and then 3p6, and then what? 4s2. So again, I only really care about the valence shell electrons. So the valence shell, we can rewrite as, if we wrote it as the noble gas, the shorthand noble gas configuration, we can very easily see the outer shell valence electrons. So for calcium, it would be argon, and then, I forgot a 2 there. So argon 4s2. So in both of these cases, our valence shell electrons are these 4s electrons. Valence shell means all electrons outside noble gas configuration. All right. And typically, at least for the main group elements, the number of valence electrons will always equal its group number, because the group number it counts up from the noble gases, so that's why that works. So for group 1, we'll have only one valence shell electron. Group 2 will have 2 valence shell electrons. Group 3, 3, 4, etc. And so it's these, what I have highlighted here, it's these valence shell electrons that are important when doing a Lewis dot structure. So let's keep going. So did I draw a Lewis dot structure for calcium? No, I didn't. So let's just draw a Lewis dot structure for calcium. So when we do a Lewis dot structure or Lewis dot symbol, you have the abbreviated element. So for calcium, you do just Ca. So I'll write that here. So abbreviated element. All right, and then you have to indicate valence electrons. And to do that, you use dots. So I'm in purple. So calcium, like I said, there are 2 outer shell valence electrons, so we indicate them with dots. So I will just show you that right here. So for calcium, it would look like this. And so these two electrons are those 4s electrons that we showed in the electron configuration. So let's just do some more examples. So let's think about lithium. If we write out the electron configuration of lithium, it is 1s2, 2s1. Or remember, we can write out its noble gas configuration. So for lithium, it would be a helium core and a 2s1 electron. So I have bolded or underlined here that what I have highlighted, this is the valence electron. All right. So what do I want to say here? So so what I want to say here is that lithium is group 1A. So this means that there's one valence electron, which we can see here. That's why I have that that highlighted. We have uh, um, one valence electron because it is a 1A element. All right, so to write out the the Lewis structure, we just write um, its abbreviated, the abbreviated element, and now we just indicate one electron, sorry, one valence electron on lithium. So we can just stick it right there. Or we can, it doesn't matter really where you put it. Typically, we try to keep the electrons kind of within this imaginary box of lithium. So you could also write it like this, or like this, or like this. It doesn't really matter. We're just indicating that there's one valence electron. So any of these would work. So let's do another example, neon. So neon, here is its electron configuration. So for neon, its shorthand electron configuration is also just neon. Or you could write it like this. You could say that there's a helium core, and then you have a 2s2 and then a 2p6 electrons, which would, oops, that's cut off. So you could also write it like this. So we could consider that these 2p6 electrons are its valence shell. That these are the outermost electrons, because even though neon is an noble gas configuration, its outermost electrons will be these electrons that are in the n equals 2 principal quantum number electrons. Those are the outermost. So neon here has eight valence electrons. You know, it is group 8. It is group 8A. What did I want to say here? Yep. And so group 8A, where all electrons in n equals 2. So that means the 2s and 2p electrons are the valence electrons. So we can think actually for this lithium example that we said that that single 2s1 electron is its valence shell. So here also the outermost electrons will have the highest n quantum number. So all electrons in n equals 2, so in this case that would be the 2s electrons, are valence electrons. Right? So if we wanted to write out a electron configuration, or sorry, a Lewis dot structure for neon, we need to indicate all 8 electrons. So we will write neon and go around neon and pair up all of those electrons to produce a Lewis structure that looks like this, where there's 8 electrons around neon. There's no other way to draw it out other than this. All right, because so if you actually wrote out the electron diagram for this, and we'll actually see this with our phosphorus example. So if we have our 2s and our 2p, all of the electrons are paired. And so we want to indicate that those electrons are paired in our Lewis dot structure. Indicate pairing. So when trying to figure out how many valence electrons there are in a certain element, definitely you want to look at highest n value, or n quantum number value, and add up electrons in that level. So that might include both the s and the p orbitals. Add up electrons. All right. So let's take a look at the Lewis dot structure for phosphorus. So remember, the first thing you do is write out the electron configuration. So for phosphorus, it is 1s2, 2s2, 2p6, 3s2, 3p3. So phosphorus's highest N is 3, N of 3. So we want to include the 3s and 3p electrons when doing our valence electron count. All right, so if we wanted to write out its noble gas configuration, we could rewrite this as, what's it? Phosphorus is neon. So it could be neon, 3s2, 3p3, and again, this also indicates our valence electrons are within this this n equals 3 group. So we have an n equals 3. This indicates that there are 5 valence electrons total. All right, so, and as written, there is 2 pairs of electrons. So, sorry, a single pair of electrons. So one pair of electrons, and then 3 single electrons. And this is evident by writing out the an electron diagram of the valence electrons. So if we were following Hund's rule here and we wanted to fill these 5 valence electrons with these the blocks here, the suborbitals within our s and p orbitals, for those 5 valence electrons, the first 2 will go within the 3s orbital. Then we will fill these bus seats up singly. The last 3 to make 5 valence electrons, so they'll fill up singly. So we want to indicate, that's a weird box. So we want to indicate electron pairs in our Lewis dot structure. Sure. So for phosphorus, we will have P for our abbreviated element, and then the 5 valence electrons. Remember, so keep in mind, we need to indicate the pairing that is also shown in the electron diagram. So you can't just start putting dots around it willy-nilly. You have to indicate the pairing. So we're going to have 2 electrons for our 3s orbital, and then it will go, oh, that looks kind of weird. Oh, come on, Notability. It'll look something like this. So we have 5 electrons around phosphorus, and then the 2 pairs, and this indicates our 3s2 electrons. All right, so when you stick electrons around the Lewis dot structure, you can't just put dots around it to your heart's content. You have to kind of think about it, and those dots actually do mean something when it comes to electron pairing. So again, keep that in mind, Hund's rule and how that works. So a couple more examples here. So for Lewis dot symbols, you have to represent electron pairing as indicated by the electron configuration, meaning following Hund's rule. So if we just do this really quickly for carbon, its electron configuration is helium, 2s2, 2p2. So carbon has its highest energy level is n equals 2. So there are 4 electrons there. So we're going to have 4 dots around carbon. So carbon's abbreviated symbol, 4 electrons. So remember in the back of your mind how those electrons will fill. 2 of them are in an s orbital, so I can draw it like this. There's 2 in that s orbital, and then 2 lonely ones in the p orbital shell. So again, kind of like phosphorus, we're going to have 2 electrons from our 2s, and then 2 electrons, something like that. 2 electrons in our p, 2 unpaired electrons. All right, so these are our unpaired. And then finally, magnesium. So for carbon, you're not going to see, if we were just writing the neutral Lewis dot symbol, you wouldn't put 4 around like each of the north, south, east, west sides of carbon. You actually have to show the electron pairing that's occurring in the 2s orbital. All right, and then so in magnesium, if we write out the electron configuration, it is neon 3s2. So its highest n level, quantum level is n equals 3. And so there are two electrons there, and they're both in the s orbital. Um, so, if I'm just keeping my pattern here, if you fill the electron diagram using Hund's rule, those two electrons, the first two will fill the 3s orbital, and there'll be no electrons in the p. So we want to indicate that, whoops, when we draw the Lewis dot structure. So you're just going to have two electrons. You could put them on the top, the bottom, but they do have to be paired. So you will not see this. You will not see those electrons on two different sides. Again, you can't just put dots around it willy-nilly. You need to indicate electron pairing. And because both of these electrons are in the 3s orbital, they have to be together on the Lewis dot structure. So I'll just put an X through that. All right. All right, let's take a look at covalent bonding. So remember, covalent bonding occurs between two nonmetal atoms versus ionic bonding, where that type of bonding occurs between a metal and a nonmetal. So what I want you to know about covalent bonding is that the electronegativities, so remember that chart from chapter 6 of all the electronegativities of atoms, or essentially atoms' tendencies to have electrons, of atoms are typically similar. So if you look at all of the atoms that make up a certain molecule and look at the electronegativities on the chart, you'll see that all of those atoms tend to have similar electronegativities. And then the bonding, when it comes to covalent bonding, is described by a sharing of electrons. And again, we call that covalent bonding. And then we can contrast that to ionic bonding, where that occurs between a metal and a nonmetal, and typically those electronegativities of the atoms that are involved, usually there is a big difference. So there's a large difference, and that's where the transfer of valence electrons occurs. So if you think back to our sodium chloride example, if you look at the electronegativity for sodium and for chloride, you'll see that there's a big difference. And then here we have an example of hydrogen, H2. H2, the bonding description that connects those two hydrogen atoms is covalent bonding. Because if we look at the electronegativity of hydrogen and we compare that to the electronegativity of hydrogen, that difference is zero because they're the same. So again, our first point here, electronegativities of the atoms are typically similar if it's the same atom that you're trying to bond. That will be covalent bonding because both of those atoms have the same electronegativity. All right. So in the simplest case, when we talk about covalent bonding, is diatomic hydrogen, or H2. So if you look at the periodic table, each hydrogen has one electron on it. If you write out the electron configuration, it is 1s1. So there's one electron. So I have the Lewis dot structure for hydrogen here. But because we're bringing together two hydrogen atoms, I've actually drawn the Lewis structure twice here. All right, and so since both nuclei are identical, have the same attraction for electrons, meaning the delta, the difference of electronegativity is equal to 0. There's no driving force for electron transfer. So, this electron isn't going to hop over onto this hydrogen. No. So what's actually going to happen is that both of these electrons will share, or each of the hydrogen atoms will share one electron with the other. And you will get something that looks like this instead, where you're essentially those two electrons are coming together and being shared. So you could draw it like this, or maybe you might want to draw it like this. Maybe that's better. But either way, both how I've drawn these two electron pairs, now they're being shared amongst these hydrogens. So now there is a covalent bond between those hydrogens. So typically we draw it with a line between it. So that covalent bond or that covalent bond or electron pair we typically draw as a line like this. All right, so that's what happens when you bring two hydrogen atoms together, close enough together. Each of those lonely 1s1 electrons will share with one another. So now each hydrogen has 2 electrons since they're being shared. So here's another way to look at it. So here's a graph. On the x-axis, we have internuclear distance. So this is essentially just distance between two hydrogen atoms. So on the right side, the two atoms are far away, and then on the left side, when it goes uh, goes towards zero or far away, when it goes through zero, those atoms are close together. So this red line indicates the energy of the system based upon how close you bring those two hydrogen atoms close together. So over on the right side, on the far side, if you have two hydrogen atoms that aren't very close to one another, neither atom feels any type of attraction or any type of repulsion, so energy is zero. There's no driving force that's going to bring them together. They're just going to move sporadically, whatever. Those two atoms aren't going to associate with one another. But see what happens as we bring those two atoms together. Once it gets to a certain part, now we're actually stabilizing the system when those two electrons, those two atoms start to share electrons. So what's happening is that those electrons are fulfilling each hydrogen's octet. So there's this stabilization that occurs. And then we bottom out essentially at this bottom portion of the well of this graph is the most stable hydrogen-hydrogen distance. So this is the H2 that we typically think about, two hydrogen atoms bonded together at a certain bond length. So this value, this distance is 0.74 what picometers? Picometers. All right, that is the measured hydrogen-hydrogen distance of an H2 molecule. It's where you have the most stable hydrogen-hydrogen internuclear distance, that the system is most stable at this point. And now if you look at the graph, so at this point where the nuclei are 0.74 picometers separated from one another, you get this stabilization from the electrons being shared and those hydrogens fulfilling those octets. So we're at less than we're at 0.74 picometers. But what happens if you start to bring those atoms closer and closer together? Well, you see that the energy spikes up. The atom doesn't want you to do that. It's gonna cost more energy to put those atoms close together. Why does that happen? It's because we have these huge nuclei that contain a proton. So now, as you're bringing those two protons closer and closer together, the proton on the one hydrogen atom and the proton on the other hydrogen atom, there's a repulsion there because they're two protons. Those two protons get closer and closer together, and there's going to be repulsion that essentially increases the energy of the system. So this rise in energy comes from repulsion of H nuclei, of the two of them, the two hydrogen nuclei. So I think the next slide talks about the different types of energies we see when we have electrons and protons in the system. So just to summarize, the two hydrogen, so H2 molecule has two electrons shared by the two atoms. So here's the Lewis structure of hydrogen. Those electrons share with one another, and you get our H2 molecule, where two electrons are being shared to form a covalent bond. And so you can see if I just draw a box, each hydrogen now has a stable 1s2 configuration. So this is the helium noble gas configuration. So if I just took a look at this hydrogen, take that Lewis structure and work backwards to what electron configuration that is. So this hydrogen that pink hydrogen has a 1s2 configuration because it gained another electron from that other hydrogen. Versus, let's do a different color. If you take a look at this hydrogen, the electrons, the Lewis structure of just that hydrogen, you can also see that there's also two electrons there because is um, it is gaining another electron from the other hydrogen because they're sharing. Also has a 1s2 or noble gas configuration um, electron configuration. All right. So in that previous slide with the graph, I talked about attraction of the electrons and stability that we get. So essentially, this graph just kind of summarizes that we find um, a balance between um, attraction and repulsion. So when we balance that, then we get a 0.74 picometer, hydrogen distance is where that balance occurs between attraction and repulsion. Because as you bring these two hydrogen atoms together, right, one of the electrons on the hydrogen is going to feel attraction between one nucleus and the other nucleus because now they're being shared. And while the other electron from whatever hydrogen will also feel attraction from both because they're being shared. So that's an attractive force that will lower the energy of the system, making it more stable. So you would think, okay, let's just try to make as much attractive force as possible and bring everything closer together. But now remember, we have positive nuclei for both hydrogens. So the closer you bring everything together, what's going to happen is you're going to have this repulsive force from the two hydrogen centers. That's what these blue lines are. So the closer you bring everything together, the more you increase this repulsive force. So that will actually increase the energy of the system. If you're looking back at this graph, um, repulsive forces increases energy, and so the system becomes less stable. All right. So if we kind of think of this diagram and think of the attractive versus repulsive forces, you can kind of think as we go along this graph. We have two hydrogen atoms and we're bringing them closer and closer together. The graph starts to dip down because attractive forces between electrons and nuclei start to take over. And then at the base, at the bottom well of the energy curve, we have a balance, or you can say we have the most attractive forces. We have most attractive and least repulsive forces. But then as we keep going and bring the hydrogen atoms closer and closer to one another, now repulsive forces take over. Forces take over. All right, so that's how this energy diagram relates to this representation of attraction and repulsive forces between two hydrogen atoms. This is the most simple case, but you could apply it to anything. This is what defines bond length. It's a balance between attractive and repulsive forces between the atoms as they come together to form bonds. All right, and then finally, in summary, with Lewis structures with covalent bonds where we share those electrons. So we drew our hydrogen, our diatomic hydrogen, like this, where we have an electron pair. All right, or we drew it like this. Right, but how you'll see it in textbooks and almost everywhere is that a bond pair is shown by a dash. So this dash is two electrons forming a covalent bond. So whether you depict diatomic hydrogen like this with an H showing the bond, or you could just write it simply as the molecular formula. It depends. Whatever the question asks. If it asks for the Lewis structure for diatomic hydrogen, then this is what you the H dash H is what you would write because you want to indicate electron pairing. All right. Okay, so let's